And we are coming actually for the next part, the back propagation and automatic differentiation. In many machine learning applications, we need to find a good model parameter by performing gradient descent. Okay, which relies on the fact that we can compute the gradient of a learning objective with respect to the parameter of the model. For a given objective function, we can obtain the gradient with respect to the model parameters using calculus and applying the chain rule. We already had a taste in section 5.3 when we look at the gradient of a squared loss with respect to parameter of a linear regression just now. Okay, so now consider this function fx square root of x to the power of 2 plus exponential x2 plus cos x2 plus exponential x2 by application of the chain rule and noting that the differentiation is linear. We compute the gradient as f x as if you solve this, then you will get something like this in equation 5.110. Alright, and then writing out the gradient in this explicit way is often impractical since it's often result in a very lengthy expression for a derivative. Okay, I don't know about you, but when I look into this expression, this equation, I feel too lengthy, right? Okay, so in practice, it means that if we are not careful, the implementation of the gradient could be significantly more expensive than computing the function, which impose unnecessary overhead. For training deep neural network model, the backpropagation algorithm is an efficient way to compute the gradient of an error function with respect to the parameter of the model. So basically what we talk about here is we would like to find the objective function. The objective function is if let's say, okay, I will just give you some idea. If let's say this is a model, this is something that you would like to have. Alright, so this is the aim, perhaps. And then you have a cloud of data. Okay, you have so many data here, so many data. So now, from this data, perhaps you can get this form, and also perhaps maybe you can also get and this form too, or from data you perhaps can get some straight line or maybe this form. So we are what is the function of objective function here? The function of the objective function here is to identify which shape that has very small error. So that function will be used to identify, to detect from these many model here, which one is actually can at least approximate the one that we want here. Alright, so we will do some comparison. The easiest way to see is we will compare this form with the one that we want, and then we will find the error. Okay, whether the error is high or not. Okay, and then we have the second shape. We compare. Okay, what about the error? The third one, the fourth one. Okay, so that is the function of the objective function. That function will be used to identify which one the output here is similar to the one we want. It may not exactly similar, but which one has the least error. Right? Okay, so that will be the meaning of the objective function. So that's why in this case, because to train the deep neural network model, in this statement here, it says that the backpropagation algorithm is an efficient way to compute the gradient of an error function with respect to the parameters of the model. So basically, we will use the backpropagation algorithm to create our objective function. Okay, so now we move the gradients in a deep network. This is basically a general knowledge for you. You will look into this technique, these things, I think, in AI in games. Alright, so you will learn more. But at least if you have this idea, it will be easy for you to understand more. Okay, alright. An area where the chain rule is used to an extreme is deep learning, where the function value y is computed as a many level function composition like this one. Wow, alright. Where x is the input, for example, the images, and y are the observations or the class label. And every function f, I equal to 1 until k, possess its own parameters. Okay? So in neural network with multiple layers, we have function fi xi minus 1 is equivalent to lambda kot dia sini. ai minus 1 xi minus 1 plus bi minus 1 this is in the ith layer. Here the xi minus 1 is the output of layer I minus 1 and mu is an activation function such as the logistic sigmoid. Oh, this one we call it as sigmoid. 1 over 1 plus e to the power of minus x, tenth or a rectified linear unit. In order to train this model, we require the gradient of a loss function L with respect to all model parameters aj, bj for j equal to 1 until k. This also requires us to compute the gradient of L with respect to the inputs of each layer. For example, if we have input x and observation y and a network structure defined by this function, let's see in this figure 5.8, forward pass in a multi-layer network to compute the loss L as a function of the input. So this is our input and the parameter a, I, b, I. This is the parameter we have, and these are the list of function that we have. So we may be interested in finding the a, I, b, j for j equal to 0 until k minus such that the squared loss, this one, the L theta here, this function is minimized where theta is a0, b0 until ak1 until bk1. So this loss error, this loss function also can be used to find the least error, like I explained just now, right? Okay, to obtain the gradient with respect to the parameter set q, we require the partial derivative of L with respect to the parameter theta j, a, j, b, j to each layer j equal to 0 until k minus 1. The chain rule allows us to determine the partial derivative as this. Wow. Alright, the orange term here are partial derivative of the output of a layer with respect to its input. Okay, so the k here is the output, the k minus 1 is input. Okay, whereas the blue are the partial derivative of the output of a layer with respect to its parameter. Assuming we have already computed the partial derivative, this one, then most of the computation can be reused to compute the L over theta I. The additional terms that we need to compute indicated by the boxes. And then this figure visualize that the gradient are passed backward through the network. So this is what we call as backpropagation. Okay. Okay, so now we move into the automatic differentiation. It turns out that backpropagation is a special case with a general technique in numeral called automatic differentiation. We can think of automatic as a set of techniques to numerically, in contrast to symbolically, evaluate the exact gradient of a function by working with intermediate variables and applying the chain rule. Okay. Automatic differentiation applies a series of elementary arithmetic operations such as addition and multiplication elementary function. By applying the chain rule to this operation, the gradient of quite complicated function can be computed automatically. Automatic differentiation applied to general computer program and has forward and reverse mode. These researchers give a great overview of automatic differentiation in machine learning. So if you want to know more, you can refer to this paper. Okay. Figure 5.10 here shows a simple graph representing the data flow from input x to the output y via some intermediate variables a, b. If we were to compute the derivative of dy over dx, we would do the chain rule and we will obtain this one. Okay. We want to compute the dy dx. So basically the dy, we will do the differentiation of dy over db, db over da, da over dx. Then we can get the dy dx. Intuitively, Intuitively, the forward and reverse mode differ in the order of multiplication. Due to the associativity of matrix, we can choose between dy over dx in this form or this form. Okay, this is not that impact. It will not affect each other. Equation 5, this one will be the reverse mode because the gradient are propagated backward through the graph, reverse to the data flow. This one is forward. Okay, so this one is from here to here. This is 5.1 to 0. Here to here is equation 1, 5.1 to 1. Okay, so this is the example here. Let's say we consider this function f(x), okay. If we to implement a function of a computer, we will be able to save some computation by using the intermediate variables. So let's say a is equal to x to the power of 2, b exponential a, c a plus b, d, okay, e is cos c, f is equal to d plus e. So x to f, okay, this one. So this one, x to the power of 2, and then we do some, this one. Then we get a, and then from a to b, we will apply the exponential, and then from, okay. Okay, so this is the example of the intermediate variable. So if we translate all the equation from 5.1 to 3 until 5.1 to 8, alright, so we would see here, okay, so this is the input, the x is the input, and the f here is the output, right? So the input here, we will do the input will be multiplied with itself, so that's why it has a square here. So when the input we multiply with its we multiply the input with itself, then we will get an a, alright, and then we will apply the exponential to the a, we will get b, alright. So in order to get the c, we will add a and b, right? And then from the c, when we do the square root, we get the d. Alright. And then for the e, when we apply the cosine to the c, we get the e. And then we add up the d and e, we get the output. This is the same kind of thinking process that occurs when applying the chain rule. Note that the preceding set of equation requires fewer operations than a direct implementation of the function f(x). This one. Okay, as defined in 5.109. The corresponding computation graph in this figure shows the flow data and computation required to obtain the function value f. Alright? Right. Okay. The set of equations that include intermediate variables can be thought as a computation graph, a representation that is widely used in implementation of neural network software libraries. We can directly compute the derivative of the intermediate variables with respect to their corresponding inputs by recalling definitions of the derivative of the function. We obtain the following. So if we apply the derivative to these intermediate variables here, then we will get as this. Right. So basically from this equation here, 5.123 until 5.128, which actually represent this one. Right. So by looking at the computation graph in this, we can compute the partial derivative of f over x by working backward. Alright. So here, first of all, we will do the partial derivative of f with c. Alright, and then we do the f with b, and then from here we get the a, and then from the a we get the x. Note that we implicitly apply the chain rule to obtain the partial derivative of f over x by substitute the result of the derivative of the elementary function. We will get like this. By thinking of each of the derivative above as variable, we observe that the computation required for calculating the derivative is of similar complexity as the computation of the function itself. This is quite counterintuitive since the mathematical expression for the partial derivative of f over x is significantly more computed than the mathematical expression of the function in 5.109. Right? Okay. So this is basically the automatic differentiations. You can just read here. Read this for your knowledge. Thank you.